we'll start discussing switch-based power amplifiers, and the simplest and most widely uh, studied and used is Class D power amplifier. So in the linear class, we saw that when we kept on reducing the conduction angle, the efficiency increased. But problem was that the power delivered to the load also decreases. And if you want to keep the power delivered to the load constant, you will have to provide lot of input power. So that is the disadvantage. Second is that the voltage and the current stress that MOS has to undergo for those classes, they are also very high. So we try to sort out those issues in this class D power amplifier, where we will see that efficiency will be very high, in fact 100%, and the stress also will not be uh, very high. I mean, less than what we encounter in linear classes. And at the same time, power delivered to the load will also be substantial. So under this class D category, we will study two types of circuits, two different versions. In fact, there are various versions available. So first, the circuit that we will study is called half bridge class D. So we will study this circuit for the efficiency, output power, and stress. So first we will see the circuit diagram of this circuit, and this implies two MOS. But then we use one transformer. So here note down the polarity of the transformer, and the winding in the primary and each of the secondary are equal. So this is how we define the VGS, voltage of gate with respect to source. This has to be kept in mind so that we can correctly predict which of the MOS is on or off. So we have two MOS, M1 and M2. So here both M1 and M2, they are made to operate as switch. So we will assume that they are the ideal switch. They suddenly turn on and suddenly turn off. And this common point, which is the source of the first MOS, will be designated as S1. And here we have drain 1, and this is source 2. Since we want M1 and M2 to act like a switch, so they should be driven by, that means the gate to source voltage for these two cases, they should be large signal, ideally square wave. So this VI is square wave, or it should be large amplitude sinusoid. So we are going to take this case, that means VI is square wave. So that then implies that this VGS1 and VGS2, they are going to be also square wave. Of the same amplitude as the VI. So we can just see the input waveforms, because these are what we will be using later on for analyzing the circuit. Say this is Vi, with amplitude say A plus, changing between plus A and minus A. So then what will be VGS1 and VGS2? So VGS1 is going to be same as input. It will be in same phase. Here you can see the polarity. So if this is plus, this is also going to be plus. But for this case, source is going to be at higher polarity compared with the gate. So that is why VGS2 is going to be of opposite phase. Okay. So what we see here is that whenever for the first half, VGS1 is greater than 0, implying that M1 is going to be on. And for the first half, VGS2 is negative. That implies that M2 is going to be off. And this scenario will keep on changing. So here we have now, so in the second half, M1 will become off and M2 is going to be on. But here we have this as on and this as off. So this will keep on changing. So what happens when these switches turn on and off? So here you can see that this point, source 1 node, when M1 is on, gets short circuited with D1. And in that case, it will be isolated from source 2, which is ground. When M2 switches on, this source 1 gets connected to source 2, short circuited, but isolated from D1. So if we draw the equivalent circuit, then what we are going to get is this circuit. So here we have VDD. So here we have node D1. And there is a switch between node D1 and node S1. And then again, a switch between S1 and S2, which is grounded. And our load network is connected to S1. So what we see is for the first half, the scenario is that M1 is on, M2 is off. So for this case, circuit reduces to this one. Yeah. So we find that at this moment, the node S1 is at VDD. For the second half, M1 is going to be off and M2 is going to be on. So for this half, the circuit is like this. So now we find that voltage of node S is 0. So here Vs1 is 0 and here Vs1 is equal to VDD. And circuit will keep on switching from one of this circuit to the other circuit. That means the voltage of the node S1 will keep on flipping between VDD and 0. So now we can further simplify this and say that equivalent scenario is something like this. That we have series LCR circuit, and this circuit is sort of being driven by a source which we will be calling as V switch of square nature between 0 and VDD. Right. So we can say that now we have a source, a square wave source, which is exciting these two or this LCR, and it switches between VDD and 0. So our LCR is being driven by this kind of source. So our objective is to find the drain efficiency. So for this, we have to find out PL, which is going to be say fundamental current to the load, or maybe the fundamental voltage to the load, and PDC is going to be VDD, because this is the DC source. From here we have to find out how much DC current is being drawn. So here we can see that finding out the drain efficiency implies finding IDC, the DC current that is being drawn, and the fundamental current, or equivalently the fundamental voltage, whichever we can find easily. So now let us see that what is IDC. So here we have circuit. So there is going to be DC current that will be drawn from this supply, and that supply DC current is going to be what we will be requiring for the drain efficiency calculation. Now, what about the fundamental? So here we see that ultimately, because of this LC, there will be fundamental current flowing through this, because only at one frequency there will be zero impedance offered by this series LC. So there will be fundamental current flowing through this load. So we have to find out what is this fundamental current and this DC. Now, when we analyze the circuit, we found that ultimately it is this circuit which we have to study. So for this circuit, we have to now find out this DC and the fundamental current or fundamental voltage. And the fundamental current through here is going to be sinusoidal. So we have already seen that the source is this one. So when we have this source, we can write its Fourier component. So this will be, there will be of course a DD, because this is between 0 and VDD. Here once again theta is equal to omega t. So what we see here is that there are infinitely many components. That means here we can see that, interpret that this source is sum of so many sources. And the first source is DC. Then there is a fundamental source, and there is a third harmonic source, and there is fifth harmonic source, so on and so forth. Okay, so now let us see that what will be the circuit for each of these components of the total switch voltage. So when DC get activated, or when we look at the circuit, this one circuit, equivalent circuit for the DC, then we know that inductor is going to be short circuit, but capacitor is going to act like open circuit, and resistor will be there. So we see that there is going to be no DC current. IDC is going to be 0 through the load. So this might pose question to that then how come we can have the DC flowing from VDD, which we will be using for finding out the DC power drawn. So we will come to that part later on. So we see that there is no DC through RLC network because of the capacitor. Now, so this is for DC source. Now when we take the fundamental, this one, so then scenario is like this. So we have here a sinusoidal of V1, and this fundamental is defined as the fundamental where the LC is going to offer 0 impedance. So this is the definition of the fundamental. So ZLC is equal to 0. So that will imply omega is equal to 1 by square root LC. So here obviously a fundamental current will flow I1, and then we can quickly calculate what will be I1. This will be simply V1 by RL. And then we can see that V1 is VDD into 2 pi. So this becomes 2 VDD by pi into RL. So this is the fundamental that will be flowing through RL. Now what about these higher order harmonics? So here we know that when the harmonics order increases, the frequency actually increases. So this n actually gets multiplied with the omega. So the circuit is this one, RLC series. So here we see that the impedance or the reactance offered by this L will keep on increasing with the order of the harmonics. However, this will start offering less and less impedance. So for harmonics components, so equivalent scenario will be that here we have harmonics components Vn, where n is going to be 3, 5, 7, so on and so forth. And then we have resistor here, load, and then between these two we have L and C. So we see that C will tend to offer less impedance. So for a very high harmonics, we can represent C as a short circuit, but unfortunately the inductor is going to offer large impedance. So this is the approx circuit for the higher harmonics. So we see that this series LC will imply that higher harmonics currents do not flow through the load, and that is what we want. We want load 2 experience a pure sinusoid of frequency omega. So all the higher harmonics components current are going to be 0. So this is the scenario. So that means now the load is going to experience, this is the switch voltage, and load now we know that is going to experience pure sinusoid signal like this, right? So for finding efficiency, we needed to know the I1, so that this thing we have already found out, and VDD is anyway known. So what needs to be found out is this part, IDC. And for the DC equivalent circuit, we found that there is going to be no IDC, but no IDC through RLC, right? So now question comes that whether this IDC will exist or not, and then how to find it out. So what we have concluded here is that through RL, this kind of sinusoidal current is going to flow. So this is during the first half. During second half, it is going to be negative, then positive during the third half, so on and so forth. So now how these currents flow, because you recall that the first equivalent circuit that we showed for the class D network is this. So here we are seeing that we have a current I1 like this, VDD. So we have to see that how this current now flows through this switch network consisting of transistor M1 and M2. So we have two halves, first half and the second half. So for the first half, we found that this is the equivalent circuit. So now you can see that for I1 to flow, there is only one possibility during the first half. It is like this, right? So what we find is, and during the second half, this M1 is going to be open. So there is going to be no current through M1. But during the each of the positive half of the sinusoid, this sinusoid, the current will be flowing. So what we find is that if we uh, call this current as ID1, that means the total current flowing through the MOS one through its drain, then we can say that ID1 is going to look like this. Non-zero, exactly equal to the first half of the fundamental through the load, and then 0 during the second half, then again non-zero and 0. So this is ID1. Now during the second half, what will happen is that second switch will close, right? And so now this I1 must flow through this M2. So in this case, the negative half of I1 are going to always flow through M2. So if we label this current as ID2, so we find that by our convention, ID2 and I1 both are of opposite direction. ID2 plus I1 is equal to 0. So ID2 is going to be reverse of this, but actually it will be the negative half of I1. So if we plot ID2, so this is going to be 0 during the first half, but it is going to be non-zero during the second half, and then 0, then non-zero, like this. So now we see that there are three currents. ID1 flowing from drain towards node source S1, ID2 flowing away from S1 towards S2 or ground, and then I1 towards the load network. So we can now write the relation between each of these three. So we find that I1 plus ID2 is equal to ID1, and it says that I1 is basically ID2 minus, sorry, ID1 minus ID2. So when you subtract ID2 from ID1, what you are going to get is I1, right? So from the load network, there is no DC, but now if you look at each of these two, ID1 and ID2, then each of them are going to have DC. That means what it says is that in this circuit, there will always be a DC coming from VDD and then passing into ground through M2 IDC. But that DC will not flow in this direction. So now everything is visible here. No DC in the load network, but DC through M1 and M2. And the DC through M1 is going to be equal to DC through M2 because ID1 and ID2, they are of exactly same amplitude. Though there is phase shift, the phase shift will have no impact on the DC content of ID1 or ID2. So what we conclude from this analysis, the DC component required is the DC component of either ID1 or ID2. So IDC is DC in ID1 or ID2. So we can write the equation for ID1, and for this case, let us say that its amplitude is equal to this I1. So this is the peak value of the half-wave rectified part. So here ID we know that is going to be I1 into 1 by pi plus 1 by 2 cos theta plus 2 by pi, all the higher even harmonics. So therefore IDC is I1 by pi. And I1 we have already calculated here, say let us say in equation 1. So 2 VDD by pi RL into 1 by pi. So this is IDC. So now we can calculate PL. So PL is I1 square RL by 2 this is RL by 2 into 2 VDD by pi RL whole square. So this will become 2 by pi square VDD square by RL. Now, what is PDC? This is VDD into IDC, and IDC we just calculated in this equation 2. So this is VDD into 1 by pi square, sorry, 2 by pi square VDD by RL. So now if we rearrange, what we get is 2 by pi square VDD whole square by RL. So this is PDC. Now if you compare this equation 3 and 4, what we see is that both are exactly equal. So therefore, eta D for class D, which is PL by PDC, is equal to 1. That means 100%. And this should not come as a surprise because switches, they do not consume any power. So they are the ideal switch. So, but here there will be one query that what happens to the higher harmonics of ID1 and ID2. So using this interpretation, we found that there will be pure sinusoid going through the loop, but ID1 and ID2, they all will be containing so many harmonics, DC fundamental and all the even harmonics. So here we see that ID2 is a 180 degree shifted version of ID1. So what we have is ID2 is ID1 theta minus 180 degree. So if we carry out this shift, then what we will get here, you can see is that this will be unaffected. This polarity will get reversed. However, this all the even harmonics, they will again get unaffected because 180 degree shift becomes 360 degree and multiple 720 degree for the fourth one, so on and so forth. So only this component is the one whose polarity will get reversed if you shift the ID by 180 degree. So the expression now is going to be here. So now let us draw the each of these components for the circuit and see that what happens. So here we have VDD and then we have MOS, or you can look at switch also, or in the MOS version, both are equivalent. And then we have here our LC network. And this current is ID1 and this current is ID2. And we know that this ID1 flows in this fashion and ID2 flows in this fashion. So we see that ID1 and ID2, they are flowing in opposite direction through RLC. But we found that only the fundamental here have opposite sign for this ID1 and ID2. Rest all DC, IDC, I2, I4, they have exactly same polarity for the both the cases. So we can see that through this LCR, DC, DC of course cannot flow through that part, or we can look at, yes, that there is a DC flowing in this direction, but there is another DC flowing in reverse direction also simultaneously. So then they cancel out. Similarly, there is a I2 flowing towards right because of the ID1, but then there is a I2 flowing towards left because of ID2. So they cancel out. So same thing happens with the I4. So what ultimately happens is these currents, then they will be IDC will be ultimately flowing through this path from VDD to ground, right? Because through the load network, they cancel out each other's effect. Similarly, I2 will also be flowing like this, and I4, so on so forth. But it is only the fundamental which is able to flow through the load network, because for ID1 it has this direction, and for ID2 also it has this direction. So on the whole, what is flowing through this is 2 times of uh, fundamental of either this or this. So 2 times of the fundamental, which is I1 by 2 cos theta. So that turns out to be I1 cos theta. So the amplitude that RL will experience for the fundamental is I1. And that is what we had shown here also when we analyze the circuit by looking at ID1 and ID2 as the half waves. Okay, so now the question will arise that what is the voltage and current stress experienced by each of the MOS, and what is the output power capability of class D power amplifier. So now voltage stress. So voltage stress means what is the maximum voltage that each of the MOS in this circuit will experience. What is this, say VDS1? What is the maximum value of this VDS1 or VDS2? So for that, let us come to this equivalent circuit in terms of switch. So during first half, we see that M1 is short circuited. So for this case, VDS1 is 0, but VDS2 is equal to VDD. Yeah. So during first half, MOS2 experiences maximum voltage of VDD. Now during the second half, we see that VDS2 is going to be 0 because MOS2 is closed, and VDS1 is going to be equal to VDD because now source is at 0 voltage and other side we have VDD. And this scenario will keep on changing periodically. So we see that each of the two MOS, they experience a maximum of VDD voltage. So voltage experience, voltage stress for class D PA is VDD. Now, if you recall for linear class, so for example, for class A or B, so this voltage is equal to 2 VDD. So now we see that each of the transistor, they have to handle or tolerate only half of the voltage compared with the linear class. Now, what about the current stress? What is the maximum current that MOS experiences in this case, class D amplifier? So for this case, we can go to this circuit. So here we see that ID1 and ID2 are the current supported by MOS 1 and MOS 2. So the maximum current that each of the MOS has to tolerate is equal to this, say, peak value of these ID1 and ID2. And this peak value is actually equal to this I1. And this I1 arises because of the fundamental voltage of V switch 1. So this part we have already calculated here. So this is the maximum current that each of the transistor has to tolerate. 2 by pi VDD by RL. In fact, at the maximum efficiency, this is going to be not only for class B, but class C, A for all, for voltage is going to be, voltage stress is going to be always 2 VDD. But the current stress will vary for those classes. So here we see that for class D, we have 2 by pi VDD RL. But now if you see the current stress for linear classes, say for class A, then for the class A, we see that the current stress is going to be 2 VDD by RL, because the maximum voltage that load will experience is this much, and divided by load. So here we see that for class D, the maximum current stress is almost 1/3 of that of class A. So, and in fact, if you do the calculation for class C, then this turns out to be even more. So for class C, so recall for class C, the current waveform is going to be like this, a part of cosine function. So this is going to be the maximum current experienced by MOS in class C. So one can calculate this IP, and this IP will turn out to be equal to IP, the maximum current for class A multiplied by pi 1 minus cos phi divided by 2 phi minus sine 2 phi. So this will of course depend upon the conduction angle 2 phi. So for example, if we take a case of 2 phi is equal to 120 degree, so this is the conduction angle. So in this case, the efficiency for class C turns out to be 89.68%. And in this case, the peak current that will flow through the MOS will be 1.28 times that of the class A. So this is going to be 1.28 times for class A, the current that we calculated is this one. So this will be So we see that the class C, they experience the maximum current stress, and class A experiences less, and class C experiences even less. So device will be in safer zone when we use it in class D operation. Now we would like to calculate the output power capability. For class D. So here we have to calculate load power maximum divided by the maximum voltage stress, maximum current stress. But in this case, we have two MOS. So this power delivered to the load is actually contributed by both. So that is why we divide it by 2. So this is the definition for two transistor. Earlier we had only one transistor. So we can calculate this CP. First, let us calculate PL. The PL we had calculated and we found that it is constant. It is not dependent upon any external parameter like input, which is variable. So here we find it is 2 by pi square VDD square by RL. So this is also then PL max. And VD max we calculated here. The maximum voltage stress. This will turn out to be VDD. So this is VDD, and I1 max we calculated, and this is equal to 2 by pi VDD into RL. 2 by pi VDD into RL. Again, this is a maximum value independent of any external input. So therefore, the CP for this case is 1 by 2 VDD square by pi square RL, now divided by VD max, which is VDD, then I1 max, which is 2 VDD and pi RL. So if we simplify this, this will turn out to be 1 by 2 pi, and this value will be 0.16 approximately. So this is for the class D. Now if you recall the case for linear classes, so CP for class A was equal to CP for class B equal to 0.125. So which is less than CP of class D. Now what about class C? So of course for that case it will depend upon the conduction angle. But if we take the case that we just now took for 120-degree conduction angle, so for this case for 2 phi is equal to 120 degree. So for this case, this value turns out to be 0.0977. So we can see that out of all these power amplifiers that we have studied up till now, it is the class D which is uh, giving the maximum output or capability. That means load will experience substantial output power, and moreover the device stresses, they are also going to be low. So now we are going to see the second version of this class D. And that is called the full bridge class D. So advantage of this is going to be that there will be more power to the load. but we will be using 4 MOS. So we have M1 and M2. This is of course connected here. And then we have M3 and M4. So they have been named in such a way that M1, M2, they are in same state, and 3 and 4, they are in same state. And again, now all these, they will be driven by square waves, but of opposite polarity, like this. So here, all the MOS, they are going to act like a switch, and M1, M2, they will always be in same state, and M3, M4, they will also be in same state. But these two pairs, they will be in state opposite to the state of the other pair. So for example, when this one is on, the other pair is going to be off. So that means obviously the polarity of the two signals, they are going to be opposite. So if this is the polarity of VGS1, VGS1 or VGS2, then the polarity of the 3, 4 is going to be opposite, like this. So for this case, also we'd like to find out the efficiency, which you can guess possibly is going to be 100%, because all the MOS, they are acting like ideal switch, but we will calculate it. And moreover, we would also like to know what is the load power and compare this with the case of the previous circuit. So first, we would like to see that what happens to this circuit in two halves of the this gate to source voltage. So for two half, we will draw the equivalent circuit. So in this half, here we see that gate to source of 1 and 2, they are high voltage, so they will be on. Other two are going to be off. That means M1, M2 are on. So M1, M2, they are on, while M3, M4, they are going to be off. So now if we draw the circuit, this is going to be the equivalent scenario. So note that how circuit has got completed because of this combination, but M3 and M4, they are open. So we find that now there will be a current flowing through this RLC circuit in this way. So we will be calling this as ID1. Now during the second half, the scenario will be like this. So here we have VDD, 3 and 4 this time are going to be short circuited. but 1 and 2, they are going to be open like this. So this time the current that will flow is going to be in this direction. So what we see now is in the first half, this node is at VDD plus VDD, other node is at 0 volt. It is grounded. So you can say that this time it is getting excited by plus VDD. However, in the second half, the right node becomes VDD, left node becomes 0. So in this scenario, now it is getting equivalently excited by minus VDD. So the final equivalent circuit, which we will have to solve for the load power, is going to be like this. That there is a square wave source which is exciting LCR like previous case, which we will call VSW. But only thing is that now VSW is going to be between plus VDD and minus VDD. Like this. So we have already seen how to find out the fundamental. So we can write the Fourier components of this, and this time it is going to be 4 VDD by pi. There is going to be no DC because this is symmetrical about 0. Average value is 0. Right. So again, there will be no DC through this. Only fundamental will flow, for which LC will act as a short circuit. And for all the higher harmonics, again, there will be no current through this LCR because primarily because of L. So what we can do is we can find out the fundamental. So for the fundamental, this L and C combined, they will offer 0 impedance, and we have RL. So there is going to be fundamental current I1, and that is going to be V1 by RL. And V1 we can see is now 4 VDD by pi. This is the amplitude. So we can now see that my load experiences more voltage for half bridge class D case. If you recall, I1 is 2 VDD by pi. So it is now experiencing half of the voltage that it experienced for the 2 times more than the previous case. So therefore, the load power in this case, PL is I1 square RL by 2. So this will turn out to be 8 by pi square VDD square by RL. Right. So this is for full bridge case. And if you recall, for half bridge case, then this will be 2 by pi square VDD square by RL. So I missed RL here. So this is advantage of this circuit. Now one can calculate what will be drain efficiency. So PL we have already calculated here. Now we just need to find out PDC. So PDC is going to be VDD, that is the supply, multiplied by IDC. So we have to see what is the IDC. So we find that for this fundamental, sinusoidal current will flow, which has amplitude equal to this. So our load will be experiencing a current I1, and this amplitude we have calculated in terms of voltage, which is equal to 4 dD by pi RL. Now keep in mind that this is in terms of the equivalent circuit, but what happens is that during one half, current flows in this direction from left to right. For the second case, it flows in the other direction. So what is happening is, like the previous case, this ID1 and ID2, this we will be calling ID2, and previous one is ID1. Both are going to be one half of this fundamental current here. So ID1 is going to be like this, and ID2 is going to be like this. Where the amplitude is going to be that of this one, that is 4 VDD by pi RL. So DC is actually going to be DC of either ID1 or ID2. So for this case, we have already seen that the DC is going to be its IP, the peak value, divided by pi. So this will be 4 VDD by pi square RL. So therefore, the DC power is going to be VDD into 4 VDD by pi square RL. No, but this time actually DC will be contributed by this one and this one both. So total DC is actually going to be 2 times of DC of one of these two. And we see that this is equal to the load. So for full bridge case also, the drain efficiency is 100%. Right. So once again, why we had to take two DC? Because there is a one DC that will be flowing for this current that is being drawn from VDD. Then there is a DC again for this ID2, and this is also being drawn from VDD. So VDD is supplying DC current for the both the part or during the both the half. But in the half bridge circuit, DC was being supplied only for the one half. VDD was supplying only one DC.